We can't hear you, I'm sorry. Or at least I can't hear you.
Me neither.
Yeah, okay, good. Still no, sorry. Sorry, no. No, still nothing, sorry.
But you can just write it in the chat.
Yeah,
I
when
think
you
it will
write
also
in,
be streamed, right?
exactly. Write it in the chat and I'll happily read it out on your behalf. Still getting nothing, I'm afraid.
Hello.
Hey, Wenlong.
There we are.
Hello, Malte. Yeah. Yeah. Quick question. So your last example, your last slides.
That one?
So the latent symmetry, yeah. So the latent symmetry, they are only valid at the gamma point.
In this particular
brilliant,
example,
right?
yes, you could, in principle, we have not done this yet, but you could, in principle, well, evaluate the Bloch Hamiltonian different different values of k. And then if you design it carefully, it should be possible to have, let's say, a non-abelian latent symmetry at, I don't know, some other important points in your Bloch sphere. Not Bloch sphere, it's, you know. I'm not a crystal guy.
Yeah, I was just wondering, that's probably why you don't see any Dirac points. This has a C3H, C3V symmetry, but there are no Dirac points along high symmetry lines. Yeah, that's probably why. I see.
Yeah.
Yeah.
You mean that the slope, it's not conical intersection?
Oh yeah, because it happens at the very center of the Brillouin zone, so it's probably will be quadratic. But you don't see linear degeneracies like Dirac points at the boundary of, yeah, that's probably why. I was just wondering.
Yeah, I'm not sure. I would definitely investigate this. I have some more examples to play with, and then yeah.
Okay. Okay. Thank you. Amazing talk.
Great, thanks for the question. So we've got Anu's question in the chat, so I'll just read it out for the sake of the recording. So they say, so you mentioned multiple times that this works for real symmetric matrices. So their question is, if you can apply your framework more generally for Hermitian matrices, as you said that it does generalize to non-Hermitian ones.
Yes, thank you for the question, and Brent, thanks for reading it. Well, you can do this. So if your initial Hamiltonian is non-Hermitian, or let's say Hermitian but not complex, then you can still define latent symmetry over this equation. And in case that your, let's say, M would be this, I mean, the simplest case would be this. You have a reflection symmetry, so M equal this permutation matrix. And then I think, just doing it in my head, your isospectral reduction would still have to have this structure. So for a complex valued Hermitian Hamiltonian, it means that your matrix element or your structure of the Hamiltonian has to be special, such that the isospectral reduction, the off-diagonal elements are purely real. It's possible. I have seen it in several systems. And if this is the case, so if your isospectral reduction for any E has this structure, then you will have, even for a Hermitian system with complex couplings, you will have parity in the eigenvectors. Does this answer your question?
Yeah, he says, okay, thanks.
Okay.
Yeah. Wonderful. Okay, we have time for more questions. Maybe I'll chip in with one. I mean, I like the bit where you showed us the extension to periodic systems. I know you've done some stuff on quasi-crystalline stuff. So can these symmetries also be seen in quasi-crystals?
We are constantly, I mean, always from time to time, we're trying to go into this. I personally have not seen them yet. I would guess that you would need a special structure like an enhanced Fibonacci, for example, where you replace some of the sides by dimer structures or something like that, or couple different Fibonacci chains.
Yeah, sure.
It would be nice. I mean, because for quasi-crystalline systems, as far as I know, it's always difficult to find well, nice solutions on the eigenvectors or eigenstates. And if you can then have like a nice argument not based on the usual reduction scheme, but on something which really works for all values of the coupling strength, by reducing the system, this would be amazing.
Yeah, no, I agree. When you don't have Bloch's theorem helping you out, being able to deduce something from the symmetry would be super powerful.
It would be amazing.
Yeah. Cool, very nice. We have time for plenty more questions. People want to chip in. If not, I will ask another one. So, I liked that you were able to deduce from Hamiltonian models to these fully fledged wave systems. But the thing that struck me is that the wave networks you showed, the thing that they had in common with the Hamiltonian models, at least to me, was that the coupling matrices between your nodes is still somewhat sparse. And so the thing I was wondering was if that makes sense, like if you had some system like, let's say, some kind of multiple scattering thing where you've got lots of scatterers or lots of resonators and they're all interacting with each other. So in particular, you've kind of got everything interacting with everything. Does latent symmetry even make, like, is it a useful concept in that sense, in that setting?
Yes. So much I can say. It's still very much in the infancy and it's work in progress. But we're evaluating some setups where you have electromagnetism. So everything really coupled to everything. Coupled dipoles. And even then, really, where you have long-range couplings, which falls off with 1/r square, I think, you can still have latent symmetries. Meaning that the electromagnetic response, so the eigenmodes of a Green's matrix, so open system, will have parity on two particular scatterers. It's possible.
Cool.
Let's say what is more involved in these systems is a question of, can you add more scatterers without breaking latent symmetry? And this is something which gives me a headache because usually I'm a brute force guy. So what I usually do is I investigate a large number of setups and then try to make some sense out of it. But of course, if the physics involved gets very complicated, or the matrix becomes, everything is coupled to everything, and everything depends also on the individual particle positions, then it gets demanding. But I wouldn't say it's in principle impossible. So we have definitely seen latent symmetries in systems where everything is coupled to everything. It's only the question of how you can systematically design them and how can you extend them.
Cool, makes sense. Thank you.
Thank you.
Are there any more questions from the rest of the audience? I have one very small thing. It was in your definition of the like walk equivalence notion for isospectrality. You had, it was the here in 6 here, that you need this to be true for all k in some finite range. So what is n here?
N is the dimension of the matrix. But maybe I think I know where you're heading.
Okay.
So let's say if it holds for k equal 1 until n-1, then it really holds for all integer matrix powers, because there's this beautiful Cayley-Hamilton theorem, which basically states that if you have the characteristic polynomial of your matrix and then replace this integer x, or not integer, this scalar value x, so the variable x occurring in the polynomial, and you replace it by the matrix itself. Then the polynomial, so the expression gets 0, and then you can use this to construct an arbitrary large power of your matrix, simply by a polynomial of the powers from 1 to n-1. So meaning this equation 6 really holds for all k.
Yeah, awesome. Yeah, you correctly anticipated my follow-up question, which is well played. Okay, cool. So that's all the questions for me. Does anybody else have anything they want to ask? If not, then I mean, yeah, I'm sure you can always reach out to Malte either via, I think the Cassini interface has the Q&A running for a while, or if not, I'm sure you can access him via all the normal channels. So then it just remains to thank him again for this really nice talk. That gave a really nice insight into this fascinating area. And then, yeah, I don't know if Bogdan wants to promote future MetaMAT events.
Yeah, thank you very much. Thank you, Malte, and thank you, Bryn. Next week, we'll have Jean-Philippe Gobi from Le Mans. And yeah, keep in touch. Thanks all for participating. Yeah. Yeah, thanks again, guys.
Cheers. Thanks, Bogdan.
Great. Having some messages here. Okay. Thanks, guys. See you soon, Malte.
See you.
Salut Vincent. Merci d'être surpris.
So when you also worked in quasi-crystals, or?
A little bit, yeah. In the like on like continuous wave versions of them, but I really, yeah, these discrete models are really fascinating, and so I think I would like to spend more time working with them exactly as you described very nicely in your talk, using the discrete models, which are often much more well behaved but still challenging, to then figure out what's going to go on in the continuous wave problem.
Yeah,
I think is where I need to spend some time, particularly since we'd like to move towards sort of multi-dimensional quasi-crystals, in which case it becomes quite challenging quite quickly.
Yeah.
I must have sent you an email. There's an asymptotic formulation, like asymptotic model that we worked on a couple of years ago. That, as I say, is like a fully coupled thing for fully coupled like 3D scatterers, and I'm wondering if these symmetries can be seen in that setting. I'll think about it, and then I might send you an email.
Yes, definitely.
Yeah.
We can look at it together.
Yeah.
I'm always eager to find more setups.
It's super nice. I mean, the fact that you were able to do. Did the guys in Le Mans build the waveguides you were talking about?
Not yet. Let's say we did full wave simulations.
Yeah.
Yeah, the question of building, it's always well, we know that this model fits very well the reality.
Yeah. Yeah, sure.
Then
Yeah,
it's
yeah.
just but we're having some other setups. So we are currently working for the scattering. We're working on transmission lines, and also on electric circuits. So
nice.
It's not scattering. There's eigenmodes then for the electric circuits, but
yeah.
Yes.
Cool. Nice. And this is what's so nice about these Hamiltonian models. It's some kind of it's really like a ubiquitous thing. Like you just you go off into whatever you want, and it should work everywhere up to some.
Yeah, and this is what I like about the spectral graph theory. Well, it just tells you, don't care about the details of your system. Just draw it as a graph or a matrix, and then play with this matrix and forget about all the physical details. And that's very fascinating.
Yeah, nice. Cool. Okay, I will sign off. I need to go and meet with a student. Yeah, no, I really enjoyed the talk. So thanks again.
Thank you.
And I'll speak to you both soon.
Yeah, thanks, guys. Have a good evening. Bye-bye.
See you.